water system armed. T-minus 10, 9, 8, 7, 6, 5, 4, 3,
What was the big discovery made by BICEP 2 in March 2014? And what is BICEP 2?
BICEP 2 stands for the Background Imaging of Cosmic Extragalactic Polarization. It's a telescope used in an experiment done in the South Pole, where the air is clean and dry, detecting weak microwave radiation from space.
In the beginning of the 20th century, astronomers noticed that galaxies were moving away from each other, and the further apart they were, the faster they moved.
Physicists theorised this meant that the universe was expanding, and that at some point in the past, it must have been very small, dense and hot. They called this idea the Big Bang.
Then in the 1960s, two astronomers discovered something called the cosmic microwave background radiation, the CMB, a faint glow or temperature that seems to permeate the entire universe.
This further supported the Big Bang because the only way two extremes of the universe could have the same temperature was if they were close enough to each other at some point in the past.
The theory traced the origins of this glow to 380,000 years after the Big Bang, the point where matter started to clump together enough for light to move around freely. But what happened before this, and how did it happen?
Inflation is the best leading theory, or group of leading theories, of how the universe came to be in those early moments of expansion. It's the mechanism, the mathematical details that explain what happens before the 380,000-year horizon of the CMB. It beautifully solved many of the problems with the theory of the Big Bang.
Like any good theory, inflation needed to make a prediction that could be tested directly. In the 1990s, more precise measurements found that the CMB is not perfectly smooth, but has ripples in it.
Inflation theorised that these ripples were the result of quantum fluctuations that were amplified when the universe expanded.
When the universe was that small, the weird world of quantum physics ruled. Energy fluctuated out of nothingness, particles popped in and out of existence, their probabilities all mixed together.
Inflation theorised that the universe expanded so fast, faster than the speed of light in that early time, that these fluctuations created ripples in the fabric of space and time.
These fluctuations expanded and formed hills and valleys in the texture of the universe that allowed matter to clump into the matter we see today.
More precisely, inflation predicted that these ripples would leave a very specific signature of light polarization on the CMB. Researchers led by John Kovac of Harvard University think they found that signature. We are now waiting for the upcoming observations by the European Space Agency's Planck Space Telescope, which is currently measuring the polarization of the CMB and is expected to report its findings in October 2004.
Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies, etc., etc. So the way in which inflation explains the bang is in terms of a very surprising feature of physics, I think very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity. But that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. And furthermore, modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsive form of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity.
At the beginning of the 20th century, the conventional wisdom in science was that the universe was static and eternal.
In 1929, that all changed. At the Mount Wilson Observatory above Los Angeles, astronomer Edwin Hubble discovered galaxies aren't stuck in one place. Not only are they moving, but they're flying away from Earth at incredible speeds. This was the first real evidence of the Big Bang.
All galaxies on average were moving away from us, and stranger still, those that were twice as far away were moving twice as fast. And those that were 3 times as far away were moving 3 times as fast, and so on. Everything was moving away from us.
It became known as Hubble's Law. His discovery is still the starting point for exploration of the Big Bang.
What Hubble convincingly demonstrated by seeing the motion of those galaxies is that the universe is expanding.
Theoretically, an expanding universe must have started from a single point.
In fact, the whole universe is expanding in all directions, getting bigger and bigger, like a balloon inflating. I admit this sounds strange, but to cosmologists, it's like winning the lottery. Because to work out where the universe came from, all we need to do is to stop time and make it run in reverse. Rewind far enough, and everything gets closer together. A lot closer together. All the galaxies, in fact, every single thing, converges to a single point, the start of everything, 13.7 billion years ago. So it's quite simple, really. Follow the clues, and we can deduce that a very long time ago, the universe simply burst into existence. An event called the Big Bang. But I'm afraid we have to stop a moment. Before we get carried away by fire and noise, at the very beginning, the Big Bang actually happened in total darkness because light didn't exist yet. To see it, we'd have needed some kind of cosmic night vision. But even this, a view from the outside, is impossible. Again, it sounds strange, but space didn't exist then either. So there was no outside. The only place there was inside. This early universe was a very strange thing indeed. There's still much I'd dearly love to know about it, but standard concepts of time or space don't really apply. it was just a very tiny, ultra-hot fog of energy. Then it expanded with a tremendous flash of radiation. From smaller than an atom to about the size of an orange in less than a trillionth of a second. Almost no time at all. The universe simply inflated into existence, unfolding, unfurling, getting bigger and cooler with every passing moment. Within 100 seconds, it was as big as our solar system, trillions of miles across. While this was happening, the pure energy of the cosmos began to cool and create matter in the form of countless trillions of subatomic particles. The first stuff there ever was. Half these particles were made of matter, the same kind of stuff which makes us. The rest were made of the opposite of matter, stuff called antimatter. When the two meet, they destroy each other in a flash of energy. It seems as if building a universe is a pretty wasteful process. Fortunately, there was just a bit more matter than antimatter. Just 1 in a billion particles of stuff survived. Which was lucky for us, because that residue is what our present-day universe is made of. You could say that we are made of the smoke of the Big Bang. By the time the cosmos was 10 minutes old, it was already thousands of light years in diameter. After that, everything spread out and cooled for about 330,000 years, when finally the fog cleared and the universe became visible.
The universe contains all the things that we can see, like stars, gas, and planets. We call these things ordinary or baryonic matter. Even though we see them all around us, the total energy density of these components is actually very small, around 5% of the total energy of the universe. So now let's talk about what the other 95% is. Just under 27% of the rest of the energy density of the universe is made up of what we call dark matter. Dark matter is only very weakly interacting with light, which means it doesn't shine or reflect light in the way that stars and planets do. But in every other way, it behaves like ordinary matter. It attracts things gravitationally. In fact, the only way we can detect this dark matter is through this gravitational interaction, how things orbit around it and how it bends light as it curves the space around it. We have yet to discover a dark matter particle, but scientists all over the world are searching for this elusive particle or particles and the effects of dark matter on the universe. But this still doesn't add up to 100%. The remaining 68% of the energy density of the universe is made up of dark energy, which is even more mysterious than dark matter. This dark energy doesn't behave like any other substance we know at all and acts more like anti-gravity force. We say that it has a gravitational pressure, which ordinary matter and dark matter do not. Instead of pulling the universe together, as we would expect gravity to do, the universe appears to be expanding apart at an ever-increasing rate. The leading idea for dark energy is that it is a cosmological constant. That means it has the strange property that it expands as the volume of space increases to keep its energy density constant. So, as the universe expands, as it is doing right now, there will be more and more dark energy. Dark matter and baryonic matter, on the other hand, don't expand with the universe and become more diluted. Because of this property of the cosmological constant, the future universe will be more and more dominated by dark energy, becoming colder and colder and expanding faster and faster. Eventually, the universe will run out of gas to form stars, and the stars themselves will run out of fuel and burn out, leaving a universe with only black holes in it. Given enough time, even these black holes will evaporate, leaving a universe that is completely cold and empty. That is what we call the heat death of the universe. While it might sound depressing, living in a universe that will end its lifetime cold and devoid of life, the end fate of our universe actually has a beautiful symmetry to its hot, fiery beginning. We call the accelerating end state of the universe a de Sitter phase, named after the Dutch mathematician Willem de Sitter. However, we also believe that the universe had another phase of de Sitter expansion in the earliest times of its life. We call this early period inflation, where, shortly after the Big Bang, the universe expanded extremely fast for a brief period. So, the universe will end in much the same state as it began, accelerating. We live at an extraordinary time in the life of the universe, where we can start to understand the universe's journey and view a history that plays itself out on the sky for all of us to see.